Welcome in this series of videos about three-phase grid converter control. These videos are part of the teaching unit Commande et interfaçage des systèmes électriques and in particular of the teaching activity Dynamique des systèmes électriques. 4 of the 6 laboratories are given by my colleague David Kempler. The 2 remaining ones are the subject of this series of videos. The idea is to give you the theoretical background and to combine with 3 guided simulation exercises using MATLAB Simulink. At the end of this series of videos, you should be able to run your code for grid converter control on the actual system. This course was developed when working at Three-Phase, a company specialized in hardware, software solutions for power electronics. All the material that is shown in this series of videos is available in the literature. In section 2 you'll find a number of references concerning ripple and grid filter design, a state space model of the LCL filter that is used, inverter and controller structures, IMC tuning, which is a tuning method for tuning PID controllers, references for space vector transformations, phase lock loops, power transfer, and finally grid converter control, which is the main topic of this series of videos. Section 3 is about grid-tied inverters. The idea is to connect these inverters to the grid and to control the bus voltage by injecting, retrieving power from the grid. We will talk about the hardware, of course, applications of these grid-tied inverters, ripple current and the LCL filter, and finally we'll propose a simplified model that can be used for control. At the end, you should be ready for the first exercise. Well, the inverters that we'll consider are three-phase half-bridge inverters. So there are 3 half-bridges, 1 per phase, of course. Each half-bridge is composed of 2 transistors, and they are of the IGBT technology, so insulated gate bipolar transistor. So you have a top transistor and a bottom transistor, and each transistor comes with its freewheel diode. The DC bus of the inverter is composed of 2 capacitors in series. Okay, so the overall capacitance will be CDC, and it's constructed that way, 2 capacitors in series, so that you have access to the middle point of your DC bus, and actually the voltage at the output of the inverter for each leg will always be with respect to the middle of this DC bus. The current flowing through each leg is available for measurement, and it's collected in this vector. You can see it's a vector because the I is in bold, and the current is defined as positive when it's flowing out of the inverter. Well, the DC bus that I've talked about before can be connected, well, either to the DC bus of another inverter, it can be connected to a DC voltage source, or it can be connected to the grid through a rectifier. Okay, and the output of the inverter, well, it could be, for instance, connected to a motor, but in our case it will be connected to an LCL filter, and this LCL filter will be connected to the grid. We'll talk about that later. Well, let us consider this first half bridge, okay, and the corresponding voltage Vinf of the first leg. Let us suppose that the top transistor is on, okay, and this means that of course the bottom transistor is off. Okay, then you can say that Vinf1, the voltage at the output of the first leg, will approximately be VDC over 2. Okay, you have something similar here. If T bottom is on, which of course means that T top is off, okay, then Vinf 1, the voltage at the output of the first leg, will be approximately minus VDC over 2. Remember that everything is referred to the middle of this DC bus. Well, let's come back to this situation here. So the top transistor is on, the bottom transistor is off, and I said, well, the voltage at the output is approximately VDC over 2. Why is this approximately? Well, this is because you have to take into account the transistor and the diode. Okay, so the situation will actually depend on the current. So suppose that EIMF 1 is positive, so the current must be flowing like this. Okay, so this means that the transistor is conducting. So we could write Vinf1 is equal to VDC over 2 minus the voltage on the transistor. So as this is small, okay, we'll neglect it and we'll write this thing here. If the current in the first leg is negative, it means a current flowing like that, and this means that the diode is conducting. So Vinf 1 voltage at the output of the first leg is VDC over 2 plus the voltage on the diode. Again, this voltage is small with respect to half of the DC bus, so of course we'll use this approximation. Well, we've seen that there is a situation where the top transistor is on and the bottom transistor is off. Okay, this leads to a voltage that is half the DC bus, and there is another situation where the bottom transistor is conducting or is on and the top transistor is off, it's not conducting, and in that case the output voltage is minus half the DC bus voltage. You can't go from this stage to this stage in one go because it takes some time for this transistor to turn off. Okay, and if you don't take this time into consideration, well, at some stage you'll have the two transistors conducting at the same time, and this will lead to a shortcut, right? So what you'll have to do is to go through an intermediate step, T top off, and the bottom transistor off. Okay, and this is what is called the switching delay. Well, in the framework of this course, this switching delay will not be taken into consideration. So you have to know that it will introduce some kind of nonlinearity. Well, in this course we'll connect this inverter to the grid, and we'll see in the application sections why we would like to do that. But anyway, we would like to control the DC bus voltage by injecting or retrieving power from the grid. And we'll consider here a three-phase inverter connected to a three-wire grid. Okay, so we're talking about a three-phase grid coupling, but the same ideas are applicable for a one-phase grid connection or a three-phase plus neutral grid connection, right? And the question is, how are we going to connect the inverter to the grid? And of course we'll have to use passive elements, and this leaves us with three choices: either a resistor or resistors, or you could use inductors, or you could use capacitors. Well, the first idea, and probably not such a good idea, is to connect your inverter to the grid through resistors. This is not a good idea, of course, because they are lossy and they dissipate energy. So the next best thing that you could do is probably connect it through an inductor. So each phase is connected to the grid through an inductor. This could work, but of course this will lead to ripple on the current, of course. So see here at the switching frequency, you'll have the voltage that is going up and down like this. Here you have VDC over 2, and here you have minus VDC over 2. So the current will do something like this. Okay, so on average it will take a certain value, but there will be ripple around this average value, and of course this ripple cannot be too high because you're exchanging power with the grid, and there are standards for that. So using just an inductor will lead to ripple, so what we'll have to do is to replace this by an LCL filter, and we'll say the details of that later on in the course, but roughly speaking, you know that this capacitor has an impedance which is 1 over CS, and this one here has an impedance L2S. So at the switching frequency, at high frequencies, this looks like a high impedance and this is a low impedance. So the ripple, which is at the switching frequency, predominantly will go this way. Okay, so this filter here, LC, will act as a filter, and the ripple that is going to be sent into the grid will be much smaller. So connecting the inverter to the grid through this LCL filter will improve ripple performance. Well, this is the overall hardware configuration for the grid-tied inverter. Remember that there are some measurements that are associated with the inverter itself, such as the voltage measurement of the DC bus and the current measurements at each leg of the inverter, and they are stacked in a vector, and they're defined, remember, as positive when flowing out of the inverter. You also have access to the grid voltage, okay, and these three voltage measurements are stacked in a vector that we'll call V-grid. You can see also in the dashed lines that there is a way to connect all this to ground, but this goes beyond the scope of this course. Well, we've seen in the course of state space control that if you would like to model an LCL filter, you need actually to put in your state vector three things. Well, the current through L1, in this case we'll call it E inverter. Okay, so this is this vector containing the three inverter currents, but you also need the current, or here the currents through L2, and these we will call E grid, and you would need the voltages across the capacitors, V cap. Okay, these are not measured and they are not available for measurement. So if you want to implement state space control, you'll have to implement an observer that is going to reconstruct these states from the available states and the measurement of the grid voltage. It's possible to do that, and state space control is considered at the end of the course, but it's not part of this series of video courses. An application of the grid-tied inverter is the active front end. The inverter on grid side is connected to another inverter which is used to control the motor. There are several advantages. In the active front end, the power flow is bidirectional. So in motor mode, the power is flowing from the grid to the motor, and in generator mode, it's flowing from the motor to the grid. This eliminates the need for a braking resistance. When the motor is braking, well, the power is simply flowing back to the grid. Note that the motor can be operated in both directions, and it can be operated in motor mode and generator mode or regeneration mode. This is sometimes called 4-quadrant operation. The alternative to the active front end is to use a rectifier, but if you use a rectifier, the current that will be drawn from the grid will be spiky. With the active front end, the current that is drawn from the grid is a nice undistorted sine-shaped current with low harmonics. There are two other advantages of the active front end. For instance, it can be used for power factor correction, and also it allows input voltage boost operation, which means that your inverter at motor side can provide a voltage that is higher than the voltage of your AC power lines. Well, another application of the grid-tied inverter is energy management. So here you have your inverter that is connected to the grid, and this is indeed a DC AC application because the DC power at the DC bus is converted into AC power at the grid level. Remember that all voltages here are with respect to the middle of the DC bus, and for energy management this grid-tied inverter is connected to another inverter, but this inverter is used for DC to DC power conversion, and this occurs also through an LCL filter, but here the voltages are with respect to the minus terminal of the DC bus. Well, the DC-DC inverter with LCL filter can be connected to solar panels, to a battery, and or a fuel cell. And then you can see that this energy management system can decide whether to inject the power coming from the solar panel or the fuel cell into the grid or into the battery. It can, for instance, inject it in first instance in the battery, and then when the price is okay, decide to inject it into the grid. Let us assume that the sun is shining, so there will be power flowing from the solar panel towards the DC-DC inverter, so there will be a current flowing towards this inverter and the DC bus voltage will increase. There is a voltage control loop in the grid-tied inverter, and its job is to maintain the DC bus voltage at a prescribed set point. When the DC bus voltage is going to increase, well, this DC bus control loop will react by injecting power into the grid in order to make sure that this DC bus voltage comes back to its prescribed set point. Well, in this subsection we'll consider ripple, and we'll first start with ripple when there is just an L circuit, and we'll see how things can be improved when you have an LCL filter. Well, if you assume only differential mode effects, so you disregard everything that is in common mode. So if you assume that the system is balanced, you can kind of write a per phase equivalent model of the system, and this is the system that you see here for the case of just an L filter. This is how it looks when you have an LCL filter. As you can see here, the transistor has been replaced by an ideal switch, and suppose here that the top transistor is closed. Okay, let's have a look at the path of the current, and we'll first assume that the inverter current is positive. Remember that when it's positive, it's flowing out of the inverter, so the way of the current will be something like that. Okay, so this is when E inverter is positive, so the current is indeed flowing through the transistor, but when the current is negative, it's actually flowing through the freewheel diode. Like this. Okay. So assume now that the bottom transistor is conducting, so T bottom is on. Then we can again look at the first case where E inverter is positive, so it's flowing out of the inverter. So this will be the path that is taken by the inverter current, and it will actually flow through the diode. If the current is negative, okay, it will flow towards the inverter and it will flow through the bottom transistor, and this is the path of the current. Well, we've seen in the previous analysis that there are situations where the top transistor is conducting and others where the bottom transistor is conducting. The rate at which this is changing is related to what is called the switching frequency, and this will be a frequency that is around 20 kilohertz. We also seen that the current E inverter is changing sign. This is of course occurring at a rate which is the grid frequency. Okay, and in Europe this is occurring at the frequency of 50 Hertz. Well, you remember that the switching frequency, which is approximately 20 kilohertz, is much higher than the grid frequency, which is 50 Hertz. So this means that over a period they switch 1 over 20,000. Well, the grid voltage, okay, which is evolving at 50 Hertz, can be assumed to be constant. Okay, it will not change a lot. Well, here you have three situations where respectively first the bottom transistor is conducting, then the top transistor is conducting, and then again the bottom transistor is conducting. When the bottom transistor is conducting, well, this point here is connected to the minus terminal of the DC bus, so the voltage over here is minus VDC over 2. You have something similar over here, minus VDC over 2. And when the top transistor is conducting, this point is connected to the plus terminal of the DC bus, so the voltage over here is VDC over 2. So for Vinf, you have kind of a square wave, okay, where you have here minus VDC over 2 and here VDC over 2. So the current in this case will be going down, then up, then down, then up. Okay, so this is E inverter, and this is again time. Well, what you see here is a simplified electrical scheme of what we've seen previously. So indeed, this is here a situation where the bottom transistor is conducting, and then the voltage Vinf is equal to minus VDC over 2. Okay, this is minus VDC over 2. And when the top transistor is conducting, Vinf is equal to VDC over 2. Well, we still have to decide on the timing. When is the top transistor going to conduct and for how long? And of course you have a similar question for the bottom transistor. Well, this timing is decided by looking at the switching period, and the switching period is 1 over the switching frequency. What I show over here are two successive switching periods. Okay, you can see it over here. And what we do is kind of decide during this switching period what is the percentage of the time that the top transistor is going to conduct, and this is then decided by this parameter, which is the duty cycle D, and D is a real number between 0 and 1. Okay, so during this switching period, percentage of the time the top transistor will be conducting, and this time will be D times the switch, and the remaining part of that time, 1 minus D times the switch, well, the bottom transistor will be conducting. And of course what you can do then is influence the average voltage that you have at the output of your inverter. And in the case situation that is drawn here, I would say that this average voltage is around 0, okay, because you see here that D is equal to 0.5. okay, so what we can do is maybe draw a certain number of other situations. Okay, so let's take a duty cycle of 0.25, so this would correspond to something like this. Okay, and there you would have that the average voltage at the output of your inverter, well, it's smaller than 0. Okay, so it's probably around minus VDC over 4. Okay, so let's draw now a situation that corresponds to D is equal to 0.75. okay, so this would correspond to something like this. And there you would have an inverter voltage, at least it's the average of that would be larger than 0, and it would probably be around VDC over 4. So what we've seen is that using the duty cycle you can decide on the width of this peak over here, and that is the percentage of the time where the top transistor is going to conduct. So we're kind of modulating the width of this pulse, hence the name pulse width modulation that you've probably encountered in other courses already. Okay, so you can kind of compute what the average output voltage will be. On average you will have D times VDC over 2 plus 1 minus D minus VDC over 2, and this gives you 2D minus 1 times VDC over 2. And indeed, if you take D equals 0, okay, this means that the bottom transistor is going to conduct all the time, that you will have minus VDC over 2. If D is equal to 1, well, then the top transistor will be conducting all the time. You have VDC over 2. D is a half, this is the situation that is drawn, okay, then of course you see that on average the output voltage will be 0. And then we had considered the situation point 25, and indeed this will lead to a output average voltage of minus VDC over 4. And then we had still to consider 0.75, and this will lead to VDC over 4. So using the duty cycle, you can kind of decide on the waveform that you have over here. Okay, so this is the inverter voltage at the output, and you can also decide on the average value of your voltage at the output of your inverter. Well, this waveform that you have here will also decide on the current. You remember that the current is 1 over L, and then you have an integrating effect, and this V here is the voltage that you see here on your inductor. When the bottom transistor is going to conduct, well, this voltage is going to be negative and the current will drop over here. When the top transistor is conducting, this voltage, this one here, will be positive, due to the integrating effect. Well, the current will increase. Okay, so you can kind of see the current waveform that you will have. Okay, and again here on a period T switch, your current will take an average value. So using your duty cycle, you can also decide on the average value of your current over a switching period, and what you will see is a kind of a ripple that is forming, and we're now going to look at the height of this ripple, or the peak to peak value of this current ripple. Well, we are now interested in the worst case ripple, okay, the peak to peak value of this ripple, and you can show, I don't want to go too much into details, that the maximum value of this ripple will be obtained in this worst case scenario where the grid frequency is around 0, okay, and where the duty cycle is around 0.5, and you see here that is indeed the situation that is drawn. And you can now kind of find this worst case ripple by remembering that EINF, okay, the inverter current, is 1 over L 1 over S, so that's the integrating effect, and then VINF. And you can see that in this worst case scenario, during a period here, that is a period of time that is T switch divided over 2, this is because the duty cycle is equal to 0.5 here, you apply a voltage of VDC over 2, okay, so you can kind of see what the value of this peak will be. It will be 1 over L, okay, this is coming from here, and then you integrate VDC over 2 for a period of T switch divided by 2, so this will be the increase of current from this point to this point. And indeed we see that the worst case ripple is obtained by this formula over here. Okay, so you see that this worst case ripple is influenced by 3 parameters. The first one is the voltage of your bus, VDC. So you could decide to decrease VDC, but this is not such a good idea, because then also you increase the maximum VINF that you can achieve. Remember that Vinf that you can achieve is between minus VDC over 2 and VDC over 2. If you decrease VDC, your achievable Vinf decreases in absolute value. Then there is of course the switching period, so you could decide to decrease the switching period or increase the switching frequency, but there again there are limits for that, because if you increase the switching frequency you also increase the losses in your inverter. A third parameter you can play with is the inductance, but again there, if you increase the inductance you make it more difficult to influence your current. Okay, so again there are limits for the inductor value, so we'll see that we'll have to do something else, and this something else is to implement an LCL filter. So this is typically the type of waveform that you see for the current at the output of your inverter. Of course there will be a component at 50 Hertz. This is because we have an AC type application, and there will be a component at the switching frequency, which will be around 20 kilohertz. Okay, and 50 Hertz, that's of course the grid frequency. Well, this high frequency component ripple is the annoying part, so we want to get rid of that, and we obtain this effect by implementing an additional LC filter. So we have a capacitor C over here and a second inductor which we'll call L2, and the idea is that at the grid frequency, okay, this will have low impedance and this will have high impedance, so preferably the component at 50 Hertz will go through the inductor. Okay, whereas at the switching frequency this impedance will be small and this impedance will be high, so the component at the switching frequency around 20 kilohertz will preferably take this way over here. Well, there will be some ripple that will go through the second inductor, but it will be small because of this impedance being very large. Okay, so the admittance, which is the inverse of the impedance, is very small over here, and you can actually compute the ripple that you have on the current E grid, which is the current that goes to the second inductor. You have to work of course at the switching frequency, okay, and then you take the original ripple that you had at the input and you have to use the formula of a current divider. So it's the admittance that you have here in L2 divided by the sum of the two admittances, and so since this admittance is small, well, there will be a small part of the ripple that will go through the second inductor, and if we write this formula you have 1 over L2 omega switch divided by 1 over L2 omega switch plus C times omega S switch. Okay, so this we can rewrite as a 1. So we multiply numerator and denominator by this quantity over here, and so we have 1 over 1 plus L2 C omega switch squared, and you remember that this is 2 pi times the switching frequency, and indeed you obtain this formula. Okay, so if your LC filter is well designed at the switching frequency, this thing here will be a high number. Okay, so this overall factor will be very small, and the residual ripple on the current at the output of your LCL filter, and the grid current will be very small. So this is the overall situation with the inverter. Remember that you have access to the voltage of your DC bus. You can measure the inverter currents, which are defined positive when leaving the inverter, and you have access to the grid voltage. And the idea will be to control the DC bus voltage by exchanging power with the grid. Okay, and for that we'll have to control the currents at frequencies that of course are larger than the grid frequency, okay, but that are lower than the switching frequencies. So the current waveforms that are produced are looking like that. So you have a component which is at the grid frequency and a high frequency ripple which is at the switching frequency, and we have designed an LCL filter that is such that, well, the path that is taken by the ripple will go like this, and the path that is taken by the component at the grid frequency will go like this. Why is that? Well, because at the switching frequency, okay, this will be a small impedance, okay, and this will be a large impedance, so the ripple current will go through here. Whereas at the grid frequency, this will be seen here as a large impedance, and this thing here will be seen as a small impedance. So at 50 Hertz at the grid frequency, the path of the current will be through the inductor. Well, we have seen that we want to control our current at frequencies that are of course above the grid frequency and at frequencies that are far lower than the switching frequency. So this ripple that you see here, it's taken care of by the LCL filter, so it does not enter our control problem, and therefore the ripple will not be considered in our model or in our control problem. We will work with this average voltage at the output of our inverter, and this is of course influenced by our duty cycle D, and in the same way we will work with the inverter currents, at least their average values over a switching period, so that we don't consider again this ripple. We're making abstraction of the voltage ripple, but also of the current ripple as well. Okay, so we are interested in the average voltage that is being applied over a switching period, and we've seen that this average voltage can be calculated using this formula, and it's of course influenced by the duty cycle. Okay, so if you desire a certain average voltage at the output of your inverter over a given switching period, okay, we will have to use this formula and turn it around. Okay, so you divide what you desire by VDC over 2. This is what is done over here. You add 1, okay, and then you multiply by a half, and you have the duty cycle that corresponds to your desired average voltage that you have at the output of your inverter. In what will follow, we'll kind of forget about this duty cycle. We'll work with a controller, okay, and this controller will have as output the average desired voltage. We won't every time write this average here or desired. We simply say Vinf, the inverter voltage, and our model will have this signal as an input. Okay, but don't forget that behind this there is always a duty cycle that is transparent in our system or in our model, but behind this, from the computed inverter voltage that comes from the controller, well, it's transformed in a duty cycle that is actually applied to the actual system. Okay, the only thing is that we won't bother to put that in our model because it doesn't bring anything. Well, we've seen that we can make abstraction of the ripple and work with a inverter voltage that is kind of averaged over a switching period, except that I won't write it like that. I will use a notation that is a little bit lighter, and I will simply denote it as Vinf, the inverter voltage that you can influence using the duty cycle. And again, in my model I will forget about this duty cycle, although it's very important to understand, of course, that in the background there is this duty cycle that is being computed from your inverter voltage, and that this duty cycle is then applied to your actual system. Okay, so your inverter system plus LCL filter can be abstracted to an LCL filter model, okay, with at the input this inverter voltage, and we'll have to add a small model of the DC bus, and we'll do that later on in the course. Well, the part of the model that involves the LCL filter is one that you know very well because it has been used as an example during the state space control problem. So the two inputs are indicated here, Vinf and Vgrid. Okay, they are indicated in orange. They are inputs. Vinf, of course, can be influenced using the duty cycle D, and Vgrid is something that you have to live with, but it can also be seen as an input. So in purple you have the three states of the system, okay, and I will also be using the current I see over here that is flowing through the capacitor, although it's not a state of the system. Well, you can write the equations, and I won't go over details. It's something that we have done before, and you obtain this three equations. It's kind of normal because you have three elements that can store energy, so you expect three differential equations, and of course you can then put that in state space format. Okay, and here you have the A matrix, okay, and here you have the B matrix. Okay, this is a 3 by 3 matrix. Since there are three elements that can store energy, you have three elements in the state vector. Okay, the two currents related to the two inductors, okay, and then the capacitor voltage, and B is 3 times 2, 3 from the number of states and 2 from the number of inputs. Well, from our state space description you can actually compute the transfer matrix, okay, and this transfer matrix will be here 2 by 2 transfer matrix, since we're considering two inputs and two outputs over here, although in our case eGrid is not really measured. This is not something you'll do by hand, but of course you can use MATLAB to compute that, and if you use the symbolic toolbox you obtain the following transfer matrix. So remember that the grid frequency is 50 Hertz, right? And that the switching frequency is approximately 20 kilohertz. Well, if the LCL filter is properly designed, you should have the resonance frequencies of the two LC filters somewhere in between. And remember, for instance, that this one over here is 1 over 2 pi, okay, 1 over the square root of L1C, and you have the same thing for this one over here, 1 over the square root of L2C. Well, we're going to assume that the bandwidth of our current controller is not pushed too far. Of course, we are going to work here with PI controllers, so this is why this bandwidth is not pushed too far. You could work with state space controllers, okay, and that could push your bandwidth over the resonance frequencies of your LC filters, okay. This is explored further on in the course, but we'll assume here that my bandwidth of my control loop is smaller than the first resonance of the LC filter, okay. So this means that we are working with frequencies that are smaller than the natural frequency of the LC filter, okay, and this is going to be 1 over L1C, for instance, okay. So if you're working at those frequencies, this is equivalent to say that in my model that we have obtained previously, these quantities here are very small, okay. And I'll show you that this leads to a very simple model where E_inf is equal to E grid, or approximately equal to E grid. So this is kind of saying that we forget about the capacitor, and this means that if we forget about the capacitor, well, you have one inductance, that is L1 plus L2, okay. So this leads to this simplified model. Well, we have seen that we don't push the bandwidth of our current controller too far, so that we can work with an approximate model. And in this approximate model, we kind of forget the high frequency dynamics, okay. And we saw that we could kind of forget this term here, this term, okay, because it was approximately zero, and you have something similar over here, okay. So this means that you can kind of forget this whole factor over here also, and you obtain an approximate model that is the following one, okay. And you have here V_inf minus V grid, okay. So you have E_inf is equal in approximation to E grid, and they are both equal to this quantity over here. So this is kind of saying that if you forget the high frequency dynamics, because we're not pushing our controller too far to have a high bandwidth, we can kind of use a simpler model for control design, and this simpler model is simply this model over here. We forget about the capacitor, and if we forget about the capacitor, you end up with an inductance which is L1 plus L2. This is V grid, and this is V_inf, okay. And of course, if you do that, you of course have E_inf is more or less equal to E grid, okay. And what you have to do is take the voltage over the inductor, V_inf minus V grid, and then integrate it and multiply by 1 over the sum of the two inductors, and this is indeed what you obtain over here. So what you see here is the hardware perspective. So you have your inverter with your LCL filter that is connected to the grid, but from a control perspective, we're not interested into the high frequency dynamics, so we can replace that by a much simpler situation where we forget about the capacitor and we end up with an inductor which is simply the sum of the two inductances L1 plus L2. Well, in reality all elements are non-ideal, so you'll have to add some kind of a resistance in series with L1 to take that into account, and you'll have to do the same thing for L2. And also the capacitor is non-ideal, so you'll have to take a resistance in parallel. And we've seen during the course on state space control how you can transform your state space description to take that into account. Well, very soon you'll have to implement this LCL filter with non-ideal elements, and I advise you not to work with the state space description, but to work as you have done previously with a number of integrators that you put on your Simulink scheme, and that you start from that and from the differential equations to construct your model. And the advantage is that you'll be able to construct a model for the three phases at the same time by using three vector integrators. So that will allow you to construct a very compact model, okay, using these three differential equations. Okay, I'm going to illustrate that. So this equation you can rewrite as follows. So it's 1 over L1, okay, times V in inf minus Vc minus RL1 E inf. Okay, so this is completely equivalent with this equation, and the way you're going to work is you're going to, well, put an integrator, vector integrator, so you're going to construct your model for the three phases at the same time. Okay, so what you'll have over here is the inf over dt. After integration you'll have, of course, your inverter current, and since this is a vector you can construct all phases at the same time. So now you take your equation that I've written over there, 1 over L1, okay, so I'll put sum over here. I take my inverter current, multiply with the gain with RL1, and I bring it over here. Okay, so what I've constructed is this part here of the differential equation, and then I will have another summator over here. Here you will have the input, the inf, okay, and here you will have minus, this thing here is Vc, and this will come from another part of the system. Okay, so if you continue constructing the model like this, using not one of the differential equations but the three of them, you can obtain a very compact model of the system that is going to model all three phases at the same time. Well, there is still one part that is lacking in our model, that's the DC bus. Okay, so we can see this DC bus as one capacitor of value C DC. The voltage is measured and is available, it's V DC, and we'll assume here that there is a resistor in parallel because this capacitor is not ideal, and we'll call it RCDC. We'll define a current IDC that is like that, it's leaving the DC bus, just as the currents are defined positive when leaving the inverter. Okay, and now what we can do is kind of make a balance of what is happening on the AC side. Okay, this is this way, and what is happening here on the DC side. Okay, and you can say that VDC times IDC is equal to the power on the AC side, and this is E inverter I, V inverter I, and you sum over all the three phases. Okay, so this is the power on the AC side, and this is the power on the DC side. And what we assume is that somewhere here there are no losses. Okay, you know, this is of course an approximation that we make to obtain a model. Okay, so now we can write the equation for the DC bus. This is simply C dC dV dC over dt is equal to the sum of the currents there leaving the capacitor. There will be also a current flowing in the resistor, so I have to put a minus sign over here, IDC, and a minus sign for the current flowing over the resistor. And this current flowing over the resistor, I'll simply write it as VDC over RC DC. Okay, so now we can kind of rewrite this as we've done previously, so that I can use it in my model. Minus IDC minus VDC over RC DC, right? So I'm now gonna start modeling that with my integrator. The output, of course, is here VDC. The input is the derivative, so I have the inverse of my capacitor of the bus. I have a summator here, and here I coming back with 1 over the resistor with a minus sign, and here I have my minus sign, and this is IDC. And the question is, how are we going to obtain this one? Okay, well, this is how I'm going to do this. I'm going to consider this power balance. Okay, this is known from my other model, and the part with the LCL filter. So if I know VDC, which is the output of my integrator, I can obtain IDC by simply taking the power on the AC side and dividing it by VDC. Okay, so this is IDC. What I have to do is divide by VDC. Okay, here I need the power on the AC side, and the power on the AC side, well, it's simply obtained by taking the scalar product of Vinf and Einf, or the product. This is going to be a product, so the output will be a vector still, and if I sum this, I have actually constructed the scalar product. Okay, so this comes from my other model, and this comes from my other model. So I take my AC power, I divide by VDC, I have the current IDC, and this allows me to construct a model of my DC bus. Okay, what you can do is initialize the voltage of your DC bus to a voltage that we'll call VDC in it.